We look up at a night sky that seems endless, a canvas of darkness that promises stillness. Yet within that silence, a paradox burns brighter than 1,000,000,000,000 suns, a speck no larger than a grain of sand, invisible to the naked eye, outshines entire galaxies. This is the quasar, the universe's most radiant secret. What are these cosmic beacons, and how do they shape the destiny of the cosmos? A black hole devours everything that ventures too close, but paradoxically, it powers the brightest light we ever observe. In the next minutes, we will follow the trail of discovery, peel back the physics, and reveal the consequences that echo across the ages. To understand the present, we must first travel back to the moment humanity first sensed the unknown. In the early 1950s, radio astronomers scanning the heavens heard a point-like signal that defied every expectation. At first, it was dismissed as a malfunction, then as a distant supernova, until the spectrum revealed a power law shape that no known object could produce. It was not a star, not a nebula, not a pulsar. Its emission flickered in X-rays. Its redshift stretched beyond any galaxy catalogued at the time. The breakthrough arrived in the early 1970s with the identification of the first quasar, 3C173, whose redshift of 0.158 proved it lay billions of light years away. Each quasar we now know is a lighthouse from the early universe, its light a message from a time when the cosmos was less than a quarter of its current age. Having uncovered the evidence, we now turn to the engine that makes such brilliance possible. At the heart of every quasar lies a supermassive black hole, millions to billions of times the mass of our sun. Surrounded by an accretion disk of superheated plasma, gravity acts as a catalyst. Matter spirals inward, shedding angular momentum, heating to millions of Kelvin, and radiating across the entire electromagnetic spectrum. While nuclear fusion converts less than 1% of mass into energy, the accretion of matter onto a black hole can achieve up to 42%, by far the most efficient natural process known. Magnetic fields twist within the disk, launching relativistic jets that pierce the host galaxy. A single jet can transport energy equivalent to 100,000 Milky Ways each year. Typical quasars consume the mass of 1,000,000 Earths annually, yet they shine for only a few 100 million years before the fuel runs dry. Thus, the brightest beacons are, paradoxically, the most voracious eaters of matter. This relentless appetite reshapes the galaxy that hosts it. But the story does not end here. If you find this unfolding mystery as compelling as I do, let me know in the comments, and consider subscribing so we can keep exploring the hidden forces that govern our universe. The next question that naturally follows is whether our own cosmic neighborhood has ever been touched by such a blinding beacon. Deep within the heart of the Milky Way lies a supermassive black hole known as Sagittarius A star, a quiet giant whose mass rivals that of a few million suns. For billions of years, it has lingered in a state of relative dormancy, feeding only on the occasional stray cloud of gas. Yet the very same physics that powers distant quasars tells us that given a sufficient influx of matter, even this modest engine could flare into a quasar-like outburst. Astronomers have identified several galaxies in the nearby universe that appear to be caught in the act of transitioning from a quiescent nucleus to an active one, suggesting that the Milky Way may one day experience a similar awakening. What would such a transformation entail for the stars, planets, and life that have taken root in the galactic disk? The answer lies in the delicate balance between radiation pressure and gravitational collapse. When a black hole erupts as a quasar, it unleashes torrents of high-energy photons and relativistic particles that heat the surrounding interstellar medium. This heating raises the thermal pressure of the gas, counteracting the pull of gravity that would otherwise cause clouds to collapse and form new stars. In effect, the galaxy's stellar nursery is placed under a cosmic lockdown, halting the birth of fresh suns for a span that can stretch across hundreds of millions of years. Existing stars, however, continue their quiet orbits, and planetary systems that have already formed remain largely untouched, shielded by the very same dust and gas that the quasar is heating. The paradox, then, is that the most violent events in the universe can act as guardians of stability by suppressing rampant star formation. Quasars prevent the galaxy from becoming overcrowded with massive, short-lived stars that would end their lives in cataclysmic supernovae. Those explosions, while spectacular, would bathe nearby worlds in lethal radiation, stripping atmospheres and sterilizing surfaces. In this sense, the quasar's murder of future stars is a form of cosmic mercy, preserving a habitable niche for the generations that follow. It is a reminder that the forces we often label as destructive are, in the grand tapestry of cosmic evolution, also agents of balance. Looking forward, the ultimate fate of our galaxy is intertwined with the slow dance of the Milky Way and its massive neighbor, Andromeda. In a few tens of billions of years, the two spirals will begin a slow, inevitable merger, a process that will reshape the distribution of stars, gas, and dark matter on scales unimaginable today. During such a collision, the central black holes of each galaxy are expected to spiral toward one another, eventually coalescing into an even more massive singularity. The gravitational waves emitted by this union will ripple through space-time, offering a new window into the most extreme physics known. Moreover, the influx of gas driven toward the newly formed core could ignite a prolonged quasar phase, bathing the merged galaxy in a luminous glow that would be visible across the observable universe. Imagine for a moment an observer situated on a distant world billions of light years away, watching the night sky of the future Milky Way Andromeda hybrid flare with the brilliance of a quasar. The light that reaches them would have traveled across the expanding cosmos, carrying with it the story of a galaxy that once nurtured life, then entered a period of quiet dormancy, only to awaken in a final, spectacular outburst before settling into a new equilibrium. Such a vision underscores the profound interconnectedness of time, space, and the physical laws that bind them. Yet, even as we contemplate these distant epochs, the tools to study them are already in our hands. Modern observatories equipped with interferometric arrays and space-borne telescopes can resolve the innermost regions of active galactic nuclei, mapping the motion of gas swirling at relativistic speeds. Spectroscopic surveys chart the distribution of quasars across cosmic history, revealing how their prevalence peaked when the universe was a few billion years old and then declined as galaxies exhausted their gas reservoirs. Computational simulations running on supercomputers recreate the birth, growth, and eventual quiescence of supermassive black holes, allowing us to test hypotheses that were once purely speculative. All of this progress rests on a simple, yet profound principle. By looking outward, we learn to look inward. The same physics that governs the most distant quasar also shapes the behavior of the black hole at the center of our own galaxy, and by extension, influences the environment in which our solar system resides. Understanding these connections not only satisfies a deep intellectual curiosity, but also informs our place in the cosmos, reminding us that we are participants in a universe that is both fragile and resilient. So, as we stand beneath a sky that appears at first glance to be an endless void, let us remember that hidden within that darkness are engines of unimaginable power, architects that have sculpted the very structure of galaxies, and custodians that have, in their own way, preserved the conditions for life to emerge. The story of quasars is far from over. Each new observation adds a chapter. Each theoretical breakthrough rewrites a paragraph. The mystery beckons, inviting us to peel back another layer of the cosmic onion. If this journey through the luminous hearts of galaxies has sparked your imagination, I would love to hear your thoughts. What do you think the next great discovery about supermassive black holes will reveal? Share your ideas in the comments below. And if you feel compelled to continue exploring the hidden forces that shape our universe, consider joining this community of curious minds. Your engagement fuels the quest for knowledge, and together we can keep pushing the boundaries of what we know.